Test, test. Hello. How's everyone doing? The sun came out for my talk. I'm not going to imply anything with that, but just saying that it's quite coincidental. Good to see everybody. Those of you eating, feel free to hang out and talk about Unicode. My name's Aaron. So I know we have like a bunch of things going on at once, so let me know if you can hear me, or I'm going to be coding some, so keep me updated on how well you can see what's going on. So today we're talking about Unicode from first principles. So any of you here, do you deal with like translated code bases at all? Yeah. So in the US, I help companies kind of learn the basics, teaching engineers the basics of internationalization. Shockingly, in America, there's not a ton of languages to have to deal with, so the companies that do need to usually need a basic tutorial. That's not what this is today. So since it's a dev conference and we're in Europe, a lot of the devs here know already the basics, and so it was a good excuse for me to get real nerdy, talk about like how Unicode is working from like hexadecimal level, and like how it's architected, why it works the way it does, what decisions were made and why, all the way up to locales, how they're going to be working. But first of all, want to talk about who I am and why I know these things. So my name's Aaron, from the US. I've been a programmer for most of my life, since I was a little kid. When I first learned about like shiny buttons, I guess. I've been into electronics and coding. I was already an engineer for a handful of years when I sort of accidentally landed on the globalization team at Nike. So they have an Amsterdam office, but they also have an office where I live in Portland, Oregon. And kind of by sheer accident, I ended up landing on that team. And the desire for Nike to build a globalization team was basically around the fact that every internal team had sort of set up their own relationships with their own vendors, and they were all using different APIs. There wasn't really any consistency or shared information. And so they said, all right, we need to hire someone in a team to be the internal point that all internal teams reference, and they use their APIs, they use their frameworks, and then that team is the one that's responsible for relaying that to a bunch of vendors. And so I was one of the first 2 hires for that team, and essentially, we became responsible for handling tens of thousands of translations a day at Nike. We supported over 25 locales. Over time, I sort of became the internal trainer of the team. So if a team said, hey, you're a new team, you're going to make a new app, go talk to Aaron about how to do that. And so I got really good at helping teams architect for a global audience with any number of locales. I got really good at learning all the edge cases of, okay, well, a lot of engineers assume they know how the BCP47 tags work, and they kind of architect their code base around incorrect assumptions of how that works. And so I got really good at that at Nike. I eventually went to another company, a US-based company called Fetch. They wanted to get ready to go international, and so I helped them go from basically 0 to multiple languages, from technical stuff, but also from a business side. So I definitely have a lot of experience talking about Unicode. I've been a speaker at the Unicode conference, and so as an engineer, I never knew how Unicode worked until I was forced into learning it. And it's like an engineering marvel, honestly, like outside of linguistics, outside of how fun it is to adapt to different cultures, technically the way it's working on the internals, I've always found really fascinating, and a lot of developers don't know about it. So that's what I want to talk about. Now I've started my own consulting business. We essentially offer fractional localization teams, so everything from implementation to translation. We help companies kind of understand, like if you are working at a company and it feels really annoying to manage your translation files, that's probably a sign that there's a better way. And so I help companies with that. We will integrate integrate anything with anything from your translation systems, whether it's a translation management system or your CMS. We do custom integration there, and generally whatever you need. I'm just kind of a localization nerd in general and love helping companies with that topic. I'm here with Lokalise, so I'm an independent contractor. Years ago, I found Lokalise on my own, and they were the best TMS I could find. A few years after that, they noticed me and said, hey, you want to be friends? And so that's kind of how we joined up. I genuinely recommend them the most. A lot of vendors in this industry like to get you to use their proprietary software that's really hard to remove later. And as an independent contractor, I find that really annoying. I usually recommend, it's best practice to keep yourself vendor agnostic. When I found Lokalise, they're a company that they do have libraries, they do have tools, but they don't try and draw you in with proprietary software. They have a lot of plain text logic, a lot of webhooks, so you can kind of keep your implementation generic. And then they keep you by good prices. They have a good way to set up your pipeline. So if you have like a repo, you can essentially integrate it to create a full cycle. So whenever you push a new code change, Lokalise can pick it up, add AI translation or whatever you want. You can have human translators, and then it makes a PR back into your repo. And so that's typically how I recommend companies set all this up. We're over at the booth over there. I've talked to some of you today, so come say hi. So today we're going to talk about, firstly, why Unicode was invented to begin with, like what was happening in the tech industry that made someone say like, oh, we need Unicode. I'm going to talk about what they decided and why they decided they needed this and how they did it. And then going to talk about how locales can affect your code base day to day. A lot of you might know some of this, but how you manage locales through like an HTTP request can really affect your code in a lot of ways. And so there's some common ways to improve how you handle those. You can automate your translation pipeline. I'm going to show an example of that using AI. So with an LLM, you can pretty easily write a script, send it up to Lokalise, have it automatically translate, and then send it back into your code base. So we're going to talk about that. And then talking about localizing dates, numbers, et cetera. Not really how to do that, that's pretty common practice, but specifically what is happening in the operating system that allows something to say, okay, well, if this is an EN locale, they prefer their dates like this. Like, where does that come from? Where does that data happen? And where do those decisions get made? So we'll be talking about that. Follow along if you want. I'm using Python. There will be a few opportunities for you to tinker around as we talk. Completely optional. And then, yeah, feel free, it's a little hard to hear in here, but feel free to scream a question at me if you have any. Would be happy to talk more about it. So we're going to start in the beginning, not of all time, but of computers. So we're all technical. We kind of know the basic history. Electricity got invented, and then suddenly we have logic gates, a 1 or a 0, turns into bits. We learned how to take those bits, put them into bytes, and it stores some piece of information. This technology was happening independently among a bunch of different countries throughout the whole world, and they were making their own decisions during that time. So in the US, they invented this thing called ASCII, and then in Japan, they invented this thing called Shift.js, and all of this was built onto the assumption of what they were independently sort of inventing. So for English, they really only had to care about 128 characters, effectively, to have a reasonably implemented machine. In Japan, they had to care about 2,000 characters. And so obviously the kanji script is a little more complicated than the US English script. In Eastern Europe, they also had 128 characters. And then in China, they had 6,000 characters, roughly, that they had to consider. And so you're in the era where 16-bit architecture, or 16-byte architecture just got kind of popular. And so all of these independent countries were using their own style of encoding that they just decided independently. And then this thing called networking happened, or the ability to share data between machines. And they very quickly learned, like, oh, well, this sequence of bytes for us doesn't mean your sequence of bytes. So you can actually see this in practice now. So I'm not going to make you all watch me type, so I have a few ready to go examples. So let's talk through this code. Can everyone see this okay? All right, so we have this byte sequence of just 93. That's essentially what the value is. In Japan, so their baseline architecture had to consider 2 byte sequences, because they had more characters that they had to consider. So just as a baseline, they invented this thing along with Microsoft called the Shift JIS encoding. And so you really can't even like output the same byte sequence with the two different encodings because they fundamentally just need more data than what the ASCII version is. So you see here I have a byte sequence of 93 and then the Japanese byte sequence, and then it goes down and it says the hex value, and so this just puts out the raw number value of that hex. And then in Western Europe, and this isn't the first version of the Western European encoding, obviously, this is the modern standard, but we're taking that byte sequence and encoding it as this encoding, and then we're doing it as Cyrillic, which is that kind of encoding, and then Shift.js. So same exact byte sequence, but by using different encoding, we're going to see that, let's see, Python, Scratch. So how's this look? So hex value of 93. That number means a quote for Western European encoding, the letter Y for Cyrillic, and I'm not sure what this kanji script is, but it means that for the Shift.js. So this is what the industry was starting to realize, like, oh, our computers can sort of start talking to each other, but we've made different decisions about like what all these like bits and bytes mean. And so that's kind of where we are. Whenever Apple, basically, they started realizing this problem, like, all right, we want to add support for Japanese language. They sent these two guys over, Apple engineers, Mark Davis, Ken Krugler, and this was later referenced by Mark Davis, who eventually came to found Unicode, as the first moment where he realized how like fundamentally different their architecture had been. So they flew over to Japan. They had a Japanese translator with them who was non-technical, and so they were talking to their fellow Japanese engineers, and the Apple engineers were on their side, and they didn't understand why, like, we're both sending 93, like, why isn't it working? And it wasn't until a lot of like effort, and even their translator had to leave, and so they started like drawing on whiteboards and just trying to communicate with these engineers in Japan about like why is this not working? And that's when they figured out like, oh, well, the kanji script has 2,000 characters, so like fundamentally their architecture in the electronics that they were building had a fundamental different understanding than what they had at Apple. And so this will later be referred to by Mark Davis as like the first time he was like, oh wow, that is complicated. I don't know how we're gonna fix that. Later in '87, Apple wanted to add kanji and Chinese script to the Apple file exchange format. This was again another instance of them saying, well, okay, now we want to add these Chinese characters, both simplified and traditional, and that's another several thousand characters that the Chinese engineers also made their own decisions around architecture. Like, what does this bit and byte mean? Eventually, in '87, a few engineers from Xerox and Apple decided, okay, we need to figure this out. We need a way to support every single like known human character and have it work across all of these systems, because this problem isn't going to go away. And so we need a universal character set. So that's really the only history we're going to get into. But this was what they came up with. So they kind of started from scratch, like, okay, well, we're in this new world of technology. How do we achieve this? So basically, everything at Unicode you're going to learn, they do it the hard way, which there's really not a better way to do it. So they got together with both English-speaking Japanese and their Chinese counterparts, and they started hand counting every single character that anyone in those languages would ever want to write. So handwriting, hand counting, saying, okay, well, just how many numbers do we need to support? We don't even know that. And so they went through the process of hand counting every single character they could think of. And that process has continued to this day. So everything the Unicode does, they work with people of that locale. They figure out like, okay, well, what do people of this locale expect? And then they write it down in a big data, and then they figure out how to technically allow for that. One thing, whenever they were designing this architecture, is you're going to see there's no such thing as a greenfield Unicode architecture. So whenever they were designing this, they needed to continue supporting the existing 16-bit kind of architecture. And so they make odd decisions basically around the 16-bit concept. So we're going to talk about that some, but they were basically not able to work in a greenfield development. That was not a thing for them. They had a lot of existing hardware that they wanted to continue to support. And so you'll see some of that architecture decisions today still. So what did they decide? They said, okay, well, we're going to reserve a massive number of, or a block of numbers. So 1.1 million is they just sort of like did their best guess, say, okay, let's just reserve this block. And it's always represented by a hex number, so 0 to 10F, whatever. So that's basically 1 million something. They divided each of this huge block of numbers into 17 planes. That's the terminology they use in the Unicode world. And it's zero-based numbering, because engineers like zero-based everything. And so that's kind of the concept. So it's not really anything special. They just said, all right, let's reserve this block of numbers, and we are going to divide them up into individual planes. So one plane can support 65-something thousand characters, and they basically go through the process of assigning a character to a number in the plane. But it gets a little more complicated, because what is a character, right? Like, what does that even mean? So in the context of Unicode, I'm going to define those, because they realized, oh, we can't just call everything a character, because it's a little more complicated than that. So they came up with these, mostly character and grapheme. Glyph is like a known concept before them, but this is what they came up with. So in the context of Unicode and encoding, a character is a technical word for it's assigned a single point within one of the planes. So, okay, this letter A, it's the 41 hex character, and that's assigned in the Unicode plane. This is also a character, because it represents one single digit that sits in one of those planes. This is also a character. So what this does is it's a way to, if you were to pass a normal letter E along with this character, you would merge them together to create an E with a tilde. We'll talk more about that later, but that's a character, but that's an example of something that isn't something you write. So it's not like a thing you would go into a writing system. It's like a technical representation that you can merge together with a different character, and you create something else. This is a skin tone character. So whenever you send an emoji and you apply a skin tone, that's using this character to say, hey, whatever byte sequence I received before this, give it this skin tone, and this is a single character that sits in the Unicode plane. And so that's how, whenever I refer to character from now on, that's going to be what I'm talking about. It's not necessarily a visual representation. It's kind of a technical representation. Grapheme is what we all typically use whenever we're saying character, just like in everyday. Usually what we're actually meaning is a grapheme. So confusingly, this is also a grapheme because it's a character, but it also happens to be the smallest single unit of writing that you can kind of conceive. Again, this is one number on one of the planes, and it is also a human language unit of writing. This is not a grapheme because this isn't something you write. This is not a grapheme because it gets merged with something else to become a grapheme, but that in itself is not a small unit of writing. A glyph. So if a grapheme is like the value of A, so it's like in a variable, so the grapheme is the value, a glyph is essentially the rendered image of it. So this is the Tahoma glyph of the A grapheme. Times New Roman, Comic Sans. These are all glyphs of the same grapheme, which happens to be one character. So it's very confusing. There's always an edge case to every single thing you think of. But these are the terminology that I'm going to be using. Any questions here? I know it makes zero sense. Okay. Okay, so those are our definitions. How is the Unicode architected to support that? The planes I mentioned, they're divided into 17 equal planes, each with 65,000 something numbers. They decided, okay, well, in plane 0, it's going to be all of our most commonly used letters or characters. And so they didn't go from 0 to 1. They adapted the number and they jumped around. So for example, within plane 0, only 85% of the numbers in plane 0 have an assigned character to it. And usually there's breaks between them. So in order to essentially make it very quick lookups for, all right, we want to render this character, and they know the architecture is typically based off of 16-byte or bit architecture, and so they place the characters in a number in a plane that makes it quick for lookups, or they make it good for legacy reasons. And so plane 0, everything that we typically do in our day-to-day lives of most emojis, but especially characters of every language, not just English, that's almost all sitting on plane 0. And then we get into plane 1. There's some historic scripts, some of the emoji you never use or whenever you're trying to be cutesy in your texts. Those random graphemes are probably somewhere on it's called the supplementary multilingual plane. Only 30% of that plane is occupied right now. Plane 2 is rare Chinese, Japanese, Korean characters. So obviously the Japanese and the Chinese and then the Korean later, they have a lot of characters, more so than myself being an English speaker can really even conceive. So they take up a big amount of space in the Unicode architecture. And so this has 92% assigned, and it's really used for historical CJK characters, so they're available, but it's not necessarily the more commonly used CJK characters. Plane 3, guess what? More CJK characters. So there's also a section of it right now that's reserved for future language support. I can't remember the name off the top of my head, but essentially whenever the Unicode consortium says, hey, we want to support this new written language, and we want to be able to have people that can write in that language, send an email, send a text in those characters. Part of the early process is to say, okay, well, where should we put it? And so they sort of put a bookmark on it before they're ready to add full support or go through all of that. So Plane 3 has some potential upcoming languages that the Unicode consortium works on, but it's 0% assigned. So there's still a handful, a lot of characters in there, but that plane is so massive that it rounds down to 0. 4 and 13, completely empty. That's a future, someday we'll add something there. So everything that we all use in our day-to-day lives is pretty much in plane 1, some in plane 2, a little bit in plane 3, and then 4 and 13 is future, and they just sort of blocked it off, which I think is rad. So we have some time in our human history using technology that all of our infrastructure that we use at the operating system level, they are technically ready to support future written languages that we don't yet have in the Unicode consortium. Plane 14, again, legacy characters. I don't super know what that is, but even whenever I say characters, there's even end of transmission or beginning of transmission characters. And so there's a lot of legacy they sort of tucked away in the plane 14. Planes 15 and 16 is what they call private use. So this is all of you in your code base. You can, let's think of maybe Apple, they let you add your own stickers or something. You can text each other different customized characters. I don't know specifically how they implemented that, but that's an example of using a private use Unicode character, is that Apple, as an organization, could say, okay, well, we have whatever 65,000 times 2 is. They have that many characters, they can agree in their own operating system is assigned this Unicode number, and it's private use, and so they can do whatever they want. They can render it any way. Any of you working in your own code base, you could say have your own font if you wanted and your own like logo, and you could say, all right, number 1,100,000 whatever is, and that's not technically correct, but you get what I mean. Somewhere on plane 15 and 16, that's our number. And you can be guaranteed that by saying, all right, that's our number, you're in one of the private use planes and you can do whatever you want with it. So let's go into a little more detail. Any questions so far? Cool. If you're interested in this stuff, I would recommend looking up this blog. I'll make sure these slides are available later. But this is a visual representation of each plane. So you can see here, the first 3 planes have a lot of space remaining. The first one is, again, what we're using in most of our day-to-day lives. This one is fewer. This one are the rare CJK scripts. And so this is just a visual representation of like how much room we have to grow with the Unicode architecture. And then again, 15, 16, these green are private use. So those will never accept characters. That will always be dedicated to a private use. I really love this specific visual, and I know the sun is out again. So this is a visual representation of, this was done a few years ago, so well before Twitter became X. They essentially analyzed every single character used in all languages in Wikipedia and all languages in Twitter. And they added a highlight when one of those characters was used. So this is a representation of how frequently plane 1 is used versus plane 2 versus plane 3. And this is like, I don't know, at the time, every single character ever rendered on Twitter and Wikipedia of all languages. So this is a good representation of like how frequently we're using just that first plane. I've mentioned this a little bit, but the process for Unicode to decide, all right, let's add a new character to the Unicode database. Like, what does that look like? So they get a new proposal. So I think maybe some of you maybe I'm just a Unicode nerd, but there's like every now and then drama around what emoji Unicode is adding next. That's the Unicode consortium accepting feedback. So you can submit your own request for Unicode to add a new emoji concept. And so they accept those requests. They have some kind of regular cadence where they meet and they say, cool, who wants to consider these emojis? And then, but beyond emojis, it's also new languages. So for example, when I was a speaker at the Unicode conference a few years ago, they had just released support for the Mayan script. And so they had gone through this entire process of breaking down like the Mayan script and how do we convert that into the Unicode planes and like where does that sit on the Unicode planes. And so all of that is done by like committee and a whole bunch of talking. They decide where it goes, again, by committee. They assign it a numerical value, and then they decide, what plane it goes on. Again, committee. And eventually, in their next release of Unicode, they release it to their Unicode character database. And what's the Unicode character database, you ask? I'm happy to tell you about it. So this is where it gets good, especially if you're a Unicode nerd like me. This is the Unicode site. Everyone has access to this. The Unicode consortium doesn't particularly have designers at the ready, so you have to be willing to look at a lot of plain text files, which is the best kind of nerd. But they have here, you can click on the latest UCD release, and we all recognize this kind of layout, so you can tell they didn't exactly put a lot of effort into this list. But this, whenever we go into UCD, this is all of the data for every single character supported by Unicode. So there's a lot of really interesting things in here. We won't go through all of them, but for example, this is like a bunch of hex values, and it's basically assigning a bunch of random stuff. I'll show you one more interesting. If we go into emoji data, so this is where the Unicode consortium, this is essentially their documentation about what every single emoji is assigned and what their related code point is on the spectrum, on the plane. And so under the hood, this information thing is named information, like an official Unicode capacity, and it's assigned this hex value of 2139. And so this is all available in a bunch of different ways. One way that I'll show you is you can download a big XML file over here. So compressed, this flat XML file is 9.6 megs. Whenever we open it up, it's going to be 200-something meg file, just like XML format. And we'll see how well my computer does here. It typically doesn't fare super well. But this is the Unicode character database. It looks fascinating, right? In here is every single character that is supported in the Unicode Consortium's database. It has a bunch of these different properties assigned to it. I'll get to those in a second. But you can see, like if I look up for one, so Latin character, capital A, it has a whole bunch of these properties that are rather nonsensical. So I'll make it a little easier to look at, show you this. So this, for example, is the entire spec for Latin capital A. And all of these properties, they mean something, so we can dig into them. So here, this is the property aliases document. So basically it says, all right, so this Latin character A has, I don't know, BC. Let's see what that means. And so we go over to property aliases, look for BC, so that means BiDi class. So that's the property for BiDi class. I don't know what its value is on. So we go over to aliases, or sorry, we go to this value, and then we say BC on so other neutral. No idea what that means, but this is what your operating system is doing whenever you are moving your cursor around, whenever you're copy and pasting code, whenever you're typing in your code editor a string. Under the hood, it says, okay, well, what's this Unicode character? And is it something that should be joined? Like, how should I render this on a screen? And so Apple, Google, they all use this exact same data to figure out, as you're going about your day, what should I do with this character? So a good example of this in practice is hello world. So whenever we double click a word, it typically automatically highlights that word. So there's Unicode properties that are telling the operating system, hey, this character here, it has this certain property, and the operating system chooses, okay, well, I should select that whole thing on a double click, I should select that whole thing on a triple click, and then if you add characters in here, and it is only selecting, like it stops at this pipe, that's because the pipe character has those properties that tells the operating system, like, hey, you should stop here whenever you double click, or whoever wants to make that decision. So let's see what our next script is. The Unicode character database, again, is bundled into all of our operating systems, all of our phones. We have access to that. And in Python, you don't even have to be part of, like, you don't have to pip install Unicode data. It's just available to you with this name of A. So whenever we run this script, it will tell us, hey, Latin capital letter A. Very boring, but it's kind of cool to know how it's all happening under the hood. And that's a direct lookup of the Unicode character database. I don't know if it's embedded in Python in this context or in Mac OS X. I'm not sure where that's coming from, but that's available to us at the operating system level. From there, we can do more interesting things. So we'll, again, do this. So let's talk about this script. So we're getting this character A. We're getting its decimal value. So we're calling this ordinal function, getting the decimal value, getting the code point of it, which is just the hexadecimal value, putting out some random information about it. So let's see what this does. All right, so character A, the decimal value is 97. The hex value is yada yada. And so we can find this direct thing if we look it up in that flat XML file. If we look up 61, I don't know if I'll make you all watch me find this, but so you can see it's referred to a lot here, and we'll say CP equals, there we go. So Latin small letter A, that's where it's coming from. It's referencing the Unicode character database, and it's getting this ordinal thing, which is like the decimal value of that character, and then it's outputting it to the screen. So if you're interested in this, it's pretty fun to type in random characters, search emoji, thumbs up. So we can sort of explore this. So that's the thumbs up emoji. It has this number on the plane. Unicode decided that's what number the emoji should be. It's probably grouped with other emoji. That's its hex value. So again, we can look that up in the UCD. And here it is, thumbs up sign. So that's what's happening under the hood. Questions so far? Cool. Let's see what happens if we were to emote. I cannot type when everyone's looking at me. So I'm going to do the thumbs up emoji, but I'm going to add my own skin tone, which is the palest option. And let's see what happens now. So we're going to run it, and we get an error. Any thoughts as to why? Remember, we're using the skin tone emoji. Yeah, 2 characters. So we can, again, explore this. If we say for car in text, we'll call this text. So now we're going to loop every character, and we're going to output that value. So you can see we have the character is the thumbs up emoji, and then we also have, I don't know why they named it the Fitzpatrick type one too, but that's the name of this Unicode character as assigned by the Unicode consortium. And again, we can look this up, and it's somewhere. I don't know if, yeah, there we go. So this is a good example of where a lot of engineers start corrupting their characters, because whenever you're looking at a single grapheme, you assume, oh, this is one character. Not true. So if you are ever doing, like, hey, give me the first 10 characters of this string, guess what? If you choose the wrong number, you've now separated the thumbs up from the skin tone. So that is a very common problem found by a lot of devs whenever they don't know why their characters are getting corrupted. So let's talk about how these characters merge together. So remember I said how this character is a character, but it's also not always. And so this is a good example. The Unicode consortium, just in the way they merged a skin tone with a thumbs up, you can do that with other characters in the Unicode database. So in this example, let me know how well you can see it, but this is an E with the dot at the bottom character. So that's one character in the UCD. This is kind of an empty placeholder, but with a thing at the top. So whenever we output this together, it's going to merge them into one grapheme. The same exact concept exists all the way down in any combination. So you can do a normal ASCII E with a bottom thing and a top thing. You can do it in any order. And so whenever we call this, it's going to render the same exact grapheme, but under the hood, it's different characters in different combinations. So let's think about this further. Let's get the length of this. So whenever we output this, these are all different lengths of strings. So again, this is one of the most common problems of corrupted characters whenever I work with companies is that if you're getting a substring, if you're getting if you're making any incorrect assumptions about a character versus a grapheme versus length, you are eventually going to come across a scenario where you cut it off at like this character, and you're going to get something the user didn't want. So how do we prevent that? Well, again, the keyword is grapheme. So the Unicode consortium has a way to do it, and it's one I don't recommend, but I'm going to demonstrate it anyway. They have this concept of normalization that we're not going to really have time to get into, unfortunately. But we're skipping over some details, but essentially what this NFC normalization does is it says, hey, for all of these characters, and these are decomposed characters that are merged into one grapheme, it's saying, hey, get the pre-composed version of it. So whatever this grapheme is, find the equivalent in the Unicode database that is only one character, and then I'm going to split it, and then I'm going to output the list of it. So whenever we do that, we see it split out. And I noticed last night when I was doing my dry run that even this example has a corruption. So this is why I don't recommend it, is because not every character that is composed has a pre-composed equivalent. So in this example, that letter E is there as one character, but if you get into other like kanji scripts, simplified traditional Chinese scripts, there doesn't exist a single character version of that script. So you're always going to have to be thinking in terms of graphemes. Every coding language has their own libraries that help you figure this out. In Python, the one I recommend is, let's find that link. It's called Grapheme, namely enough. And so I've never met this person, but I recommend their library all the time. And so if you dig into this, you can see they have a folder called Unicode Data. And tell me if this file looks familiar. So they pulled this directly from the Unicode's data. And the way this library works is that it essentially goes through, and this is another piece of the Unicode data that we didn't talk about directly. And then it also goes into this break property. So again, a break property is one of the properties that exists on every single character in the UCD. And so what this developer did is they wrote a library that loops every single Unicode character in a given string, reads those properties, and makes a decision based off of their research saying, where is the end of this character? That way they can say, okay, well, these 4 characters are decomposed, but they render into one glyph, so I'm going to stop once I get to a breakpoint according to those UCD properties. And we can demonstrate this pretty easily. And this is an external library that is unfortunately not included in Python. There are some languages that do have grapheme support out of the box. So if we integrate this, then you can see it's much more intelligent about not stopping that until the grapheme is fully rendered and it receives the character that's like, hey, I'm done, on to the next one. And so, again, they didn't really do anything special beyond looking up the Unicode data. They store it locally in their repo, and then they make decisions based off of looking through arbitrary property text files. So it's not particularly easy, but at the end of the day, it's just numbers and referencing that property. So if any of you in your code are wanting to get, extract or we want to show a summary of, 100 character string, we need 10 characters of it. You want to be using the graphemes of it, not a length of 10, or, not treating it as if every single grapheme in a string is one character. So this is the result of some corruption that almost every single developer I work with has. So is this thoughts, questions? Are any of you thinking in your code base like, oh yeah, there's definitely some chance of this happening? Note that this also accounts for whenever you're setting up a database and you set a varchar and you set a number on it, it doesn't care about graphemes. It cares about characters. And so it is very possible that if you set your database to have 100 characters allowed, and you send it 101 characters, but it's only like 90 graphemes, you will absolutely get it corrupted. Cool. There's a lot of stuff that you can do in the Unicode character database that I'm not going to have time to talk about today. One is canonical equivalence. So if you are wanting to search for something and someone types this pre-composed character of E, but in your database you have stored this decomposed set of characters, they render as the same grapheme, but they are different values. And so Unicode provides APIs where you can say, hey, give me the canonical equivalent of this set of characters versus that set of characters. So if you come across any of that, that's what you want to look for. Normalization, specifically for sorting, and I think this is supposed to be collation, not normalization, my bad. Collation is basically how do we sort whenever, not only culturally are there different expectations around some areas expect, like if you're in the context of like a phone book, they expect sorting to be different than if you're in the same locale but in a different context. Or how do you sort like A versus A with a thing on top versus A without a thing on top? You can kind of make that decision for yourself. A lot of the programming languages that you're using sort of solves this sorta, but if you are targeting a bunch of different regions, they might have different expectations about how these characters or these graphemes are sorted above or below one or the other. Encoding, I didn't really have time to get into encoding, but essentially like UTF-8, UTF-16, that's really how it's stored for long term. Unicode is how it's organized. And so encoding can definitely trip you up in a lot of ways. So the length of the characters, if you're in a JavaScript file in your code editor, that by default is UTF-16. And so the length will be different than if you were in UTF-8. That can really trip people up, especially if you're in your source code editing a file by default as UTF-16, but then you render it and encode it as UTF-8. There can always be a lot of confusion there. So quick summary, one grapheme doesn't always mean one character, but sometimes it does, edge cases. The same grapheme can be rendered using a bunch of different methods. It really just depends on how it was rendered. Some legacy is the cause of that, but you cannot always assume that it's the same characters being used. And you have access to the Unicode character database in your environments. It's built into your operating systems. Cool, so that's the UCD. That is one of a few more topics to go. Questions, thoughts? Okay, the next part of this equation is locales. So, okay, cool, we can render graphemes. How, in like our day-to-day lives, how do we represent our locales? How do we represent these expectations? This very boring white paper, actually I find it interesting and it looks very boring. This outlines the BCP 47 spec as provided by Unicode. So this is what they're following. Don't worry, I won't make us look through all of this. But what I want to point out is that we're all familiar, like en-gb is an example of a locale. A lot of engineers think that it's always going to be 2 characters, or it's always going to be, some normal format like a dash or an underscore. The BC 47 spec supports 3 different, previous ISOs. So just that EN section, that first section, has legacy support for 3 different specs. So for example, let's take a look at these. So this is the ISO 639-1. This is what most of us are familiar with, but it also is perfectly a legitimate locale to support any of these. This is the details of another spec. And then this third one, this is yet another spec. And this is only on the first language tag. So this is another thing where a lot of engineers, you've built up your architecture making an assumption about what a locale tag even is. And the reality is whenever you extend support, it's usually more complicated than you had initially thought. And so that's basically why I have a job, is saying, hey, you built your architecture, making an assumption about how this stuff works, but usually there's a lot more edge cases that engineers really even knew to consider. A lot of it is because this has been around since like POSIX. So this was like before Unicode. It is part of the original like Unix systems. And it's still used today, and it still supports a lot of those legacy things. I don't need to tell you this. This is for the American developers I usually talk to, but for our context, DE means German. DE-IT means German as spoken in Italy, English as spoken in Germany. So you can really combine these in any way, and that's not even the end of it. There can be like more dashes. You can have, like in the BCP 47 spec, it literally calls out x-whatever as a valid locale, because it really is just, they don't really care. It's just the structure of it, and it's technically like legacy support and everything. So there's a lot of ways to have a legitimate locale that engineers don't typically expect. As a quick summary, where does a locale come from? Any of us who get a device for the first time, we usually set our language. Those of you that are multilingual kind of know how to like set multiple languages. But that's the origin of where locales come from in any kind of system. Whenever you are implementing your locale, or I'm sorry, whenever you're implementing locale support in your code, the general flow, and this might be a review for some of you, but essentially from your device, whenever you set your languages, it is carried on your device. So locale is device data, not user data, because you sometimes have anonymous users. I see you. So it can be user data if you know who the user is. What's that? Sorry, man, I can't hear you. Yeah, but let's think of the context of a website. If you have someone open up your website for the very first time, how do you choose what language to show them? So that's part of their device metadata. If you know who they are, you can look up their user preference, and you can make a decision to change what their device prefers, but you will absolutely come across a scenario of an anonymous user, and what language do you decide? Do you just default to English? Like, no, that's not right. So it's device metadata. That's like how it's architected into the system. And if you have enough information to change that default setting, then that's totally fine. And users can also set a list of preferred languages. So from their phone into your service, there's this accept language header, and this is what it looks like. So it's not one locale, it's a list of preferred locales. So this part here is called the Q8. And so this user prefers Italian as the one, so that's the highest preference. And then it goes into French with a Q8 of 0.9, English has a Q8 of 0.8. So that's in every single HTTP request you're receiving in your system right now. That's part of the standard. Your system, you can say, okay, well, us as a company, we've decided we prefer, or we support ENUS, German, ES419, and French Canadian. And so you have to parse this request. It's probably happening for you in the background in your framework, but your framework is doing this for you, saying, okay, well, I'm going to split up the string, I'm going to weigh it by Q8, and then I'm going to have to decide which of these locales is the best match for my list of locales that I support. And so you're going to receive the request, you're going to resolve the locale. So that's kind of my own phrase, that's not like a known phrase, but essentially you have to decide, okay, well, this user, they do prefer English, but that's below the French preference. And so we support French Canadian, and so that's what we're going to decide to show this user. You do your database stuff, we'll get to this in a second, HTML template stuff. In your response, you include this content language, fr-ca, in your response, and that's how their device knows what language they're looking at. Questions here? So this is what your device uses to provide localization of dates. It's a little more complicated than that, but that's basically how you tell the device, hey, this is the locale I'm rendering to you, and then your browser or the operating system picks that up. One thing that I always recommend companies do is be very specific with your locale. So a lot of people say, all right, we're going to say our supported locale is EN, and then a year later, 2 years later, they decide they want to support an extra dialect of ENUS or ENGB, and that is really complicated. So whenever you do this database stuff, the reality is that this is going to end up being effectively a slug throughout your system. So it's going to be FRCA in your database scheme, depending on how you have that set up. There's going to be files named FR-CA. So I always recommend companies, if you want to be broad and you want to have broad support for like EN, you can do that in the resolve locale step, but you would do a mapping to figure out the specific one. So if I'm an app, I'm in the US, my locale will always be EN-US. If someone hits my server with an EN locale, I'm going to make that decision on the back end to say, okay, well, EN-US is what I want. But that prevents me down the road if I ever want to go more specific from EN to EN-US, I don't have to do database migrations and I don't have to rename my files. And so I always recommend companies start with a very specific locale that you are, whatever you're authoring your content in, that's your locale that you should use. And if you need to make broad decisions later, it's easier to do that in other parts of the system. Thoughts there, questions there? Cool. So we've covered the UCD, we've covered a little bit of how locales work. Now we talk about translation. Obviously, the concept of translation wasn't really related to computers at all, but we've had to figure out a technical way to do this. A translation management system is effectively, it helps with the logistics of dealing with language, dealing with locales, sending requests back and forth. Again, I'm here with Lokalise, and so there's a lot of benefits to it. And from a few conversations I've had, I've heard effectively like, yeah, we've built our own version of that. That's something I hear a lot, like, oh, we have our own internal system. It makes sense, but what I usually tell developers is that building your own TMS is sort of like building your own blogging platform. Like if it's in your own code base, sure, do whatever you want for your personal site. But the reality is of if you're at work and you say, oh, I'm going to make our own CMS because it's just a title, it's just a post, you're inevitably going to have marketing and content teams come to you saying, hey, we really want to have a date publish, or like a moment we publish our blog post, or we really want tags, or we really want editors and approvals. That same logic applies to a TMS. Like, yeah, it's just a locale and it's a value, but your content teams are eventually going to want to fix typos without you deploying. And so going through a TMS helps you on the development side not really have to deal with that. Dealing with a bunch of file formats that you don't really want to have to support. There's a lot of things that you can simplify your life by just plugging it in through a TMS. Like I mentioned for Lokalise, one of the big reasons I like them is that they price by total keys, not by word count. And so you can have an automated system that if you know you don't need this key anymore, you can save money by removing it from their system. They don't upsell you all the time. They don't really include translation services, which is a benefit because you can just push your LLM and like apply the translations through there. And they really care about this industry a lot, so that's why I really recommend them. So another coding demo of the process of translation. Has anyone used get text here? Anyone heard of that translation system? All right. So that's kind of what I have here. So let's talk about this example. I have a locale, ENUS, and then I'm looking up my local directory, and then I'm printing out hello world. So this, I won't really go into the details of get text, but this is effectively how you would output a translated string. If we look into this PO file, that's effectively what we're showing there. And we will show a quick little example. Translations example. All right, so hello Devworld, pretty easy. Whenever I make a new system, I usually want to provide translations, but I also want it to be automated and translated by LLMs. So you'll see this is a script I myself use some where I'm effectively, I have my Lokalise API key, I have the project coming in from my .in file, I have the source locale. So again, since I'm an American developer, my locale is EN US. It essentially uploads the file using the Lokalise client, all these settings, and it will push it to that system. So within Lokalise, I'm going to quickly make a new project. So I'll do new project, Devworld. I'm going to say EN US. We are in Amsterdam, so I'll do Dutch, maybe ES MX. Okay, so I'm going to take this project ID and update my in file. I heard this is live streamed, so I'm going to make sure to roll my API key later. So with this push script, I'm basically just going to upload this file to Lokalise. File uploaded. So now if I go in here, you'll see that I have my original key there. I'm just going to do Google Translate here, so you can see it applied hello Devworld. So I'm going to do my pull script now. And again, all that's doing is just downloading the file from Lokalise, and it compiles it. Get text requires you to compile your translation file, and then in theory, I should see here I have my ESMX in L. Cool. You'll notice that I also overwrite my source file. So you would think that your local source file of your authored language should be your source of truth. I recommend companies see your translation files as build assets effectively. The reason for that is that, say, whenever your marketing team or whoever logs into Lokalise and they want to make their own change even to your source file. So the developers, you don't really necessarily want to be in the job of writing content, I assume. You don't want to mess with it. You want something where your marketing team can come in and say whatever they want. Hit save. I'll clear this out. Apply Google Translate. So I'm going to do another pull. And so that's an example of you don't have to care as the developer. You would have this set up with your GitHub repo. It could automatically make a PR. But on the coding side, you could go back to example. And again, you resolve to, say, the Dutch locale. And now, in theory, you're able to output that. But again, this is still kind of an automated process. I want to be able to automatically translate with LLMs. And so with Lokalise, you can set that up automatically. So for example, I'm going to set up an automation. I'm going to create an automation rule that says effectively, hey, whenever you detect a new change to my source language, EN/US, and I want to automatically apply localized translations to this. So I'm going to check a few options. And so now, anytime I change my source file, it's going to automatically apply LLM translation. So I'm going to, from my code now, say hello from the code. And I'm again going to push. So it's going to be a bit slower this time because it's receiving the new value and then it's applying the the LLM translation, and then it's going to update it in Lokalise. So you can see now, whenever I go in here, it's going to automatically be translated. And this wasn't Google Translate this time. This was through an LLM. And so now I can pull. And now all of that exists locally in my code. So you can see, let's do ESMX. Cool. So that's an example of how you can, kind of in a scrappy way, quickly apply translations to whatever translation file formats you're using. That's usually what I do if I'm just wanting a quick project, but I'm wanting to apply translations. Of course, you can have human translators do this if you really want to, but that's the basics there. So let's go through and make this a little more complicated with some localization. I'm going to, I guess within the code, I'm going to say, hey, my favorite number is number, and the date is date. I'm going to push that into localize. It's applying the translation, and then I'll pull. So now, not only is my English updated, but in theory my ESMX and my Dutch is all there. So now I'm going to talk about localization, and specifically how it happens under the hood. So format. So I had what, number, .78, date equals datetime.now, datetime import datetime. Okay, so let's show, we're showing this in Spanish right now. And so whenever, nope, that's not what I want. Whenever we run this, all right, so we have our number output, and the date is this. Obviously, that's not localized into what they would expect in that area. So whenever I'm in a Python code base, I recommend people use Babel. So anytime I'm evaluating a library, I recommend people look up to see if it's using the Unicode standards, which I happen to know Babel is. So from babel.dates, import format date, from babel.numbers, import format. So what these do is they receive a value, and they're going to look it up from, and they're going to output it in the format expected by that locale. So format decimal, and then I'm going to pass my source locale. What is that, my locale? And again, format date locale equals my locale. Okay, so now in theory, whenever we render this, okay, so it automatically knew what the date is expected for the ESMX locale. I'll use Dutch. So you can see it automatically even translated the date. So datum is, so how does that happen? Like, what in the Unicode consortium is telling it, hey, if you receive something in this locale, this is the format that it expects. That's what we're going to cover now. So again, this is something that pre-existed, or it was rather a later invention than Unicode. It existed separately from Unicode. IBM, Apple, Microsoft were all maintaining their own like locale expectations of like locale-based data. Eventually, IBM said, hey, we'll donate our existing library over to the Unicode consortium, and that eventually became called the ICU components. And so under the hood, a lot of our systems are using the ICU components to achieve that localization. They usually, if you're seeing it, it's down at the C level, C++, Java. They're working on a Rust. It's not even close to being done yet. But the way it's architected is that the ICU library wraps around this thing called the CLDR, Common Language Data Repository. So this, again, going back to the Unicode site, this is a huge repo, a bunch of XML files of all the locale-based data that our operating systems are using to decide about what to do. So we go into common, we can go into main, and let's just look up like root. So this is the highest level kind of decision that it has. So you can see it has a whole bunch of stuff, left to right, characters, And so we can crawl through this a bit. So for example, language. We can hop into this file, and this is the Dutch file of the CLDR, and you can see where it says the Unicode consortium has made some kind of official decision that this is how English should be rendered in the Dutch language, and it has all these listed. So if any of you have ever, like, in your code figured out like some library to output, like, hey, I want all of the names of languages in this language, it comes from the CLDR. And there's a ton of stuff in here. So territories is another one. So again, territory, this is all the Dutch translations of every territory. We can choose any random locale you want, and you'll see the same thing. Calendar, that's also in here. So we got the calendar. So again, it has a bunch of different calendar support. Gregorian is the most common, and this is what the Dutch locale expects the abbreviated version of months to be. This arrow up here is kind of a refer to above indicator. So this is the translations that is provided by Unicode. So whenever you are outputting a date, it references this. Formatting, so again, date formats. This is the English version of it. And you can see this at versus like ohm. So what's happening under the hood here? Get to close all those. So if we are doing this. So right now I'm outputting a date. I'm using the intl object. So are any of you familiar with the JavaScript intl object? Probably in your code bases, if you're localizing anything, you're using that. Under the hood, this is referencing the CLDR data. So we can see, okay, well, en, it's outputting the data as this. What's it do for the Dutch locale? It's outputting it this way. And so we can track that down. We can say, all right, where is this happening? And so in the CLDR repo, you can see the maintainers of the Firefox JavaScript runtime chose that without any more information, by default, they're going to output short. And so you can see here for en, it's this pattern. In this is the wrong one, I think. Yeah, that's the long pattern. So that's what's happening at the JavaScript runtime. They're referencing the ICU library. That is referencing CLDR data, and that's how they're deciding how to render that. And obviously, you can have different preferences in how you output this. So we can say date, style, full.
Should I pull it down for your hand?
Yeah, I think I can do it.
Yep.
I say that. Is this helpful? All right, fine. You can do it. Did it wrong. It's a lot of work for like the last 2 slides. Cool. Thank you. For anyone live streaming, sorry. Reach out to me. Okay, so for translation, you probably don't want to roll your own in the work context. It's kind of a fascinating like engineering exercise just for your own stuff if you're interested in it. But if you're finding frustration with dealing with translation files and like manual editing or like launching things at the same time, or like, oh, this wasn't ready for production release, but the translations got released, there are techniques to fix that, and they're linguistic techniques. They're not engineering techniques. So reach out to me. I'm happy to talk to you about those. Your translation files should generally be seen as artifacts. So in my case, I ignore all of my translation files. I ignore them except for my source translation file. So those should be rendered as the same as your like JavaScript bundle. So they should be treated like build artifacts. LLMs make it easier to drop a bunch of like cool variables into your translation strings, but if you're dealing with human translators typically aren't very technical, so the more like fancy variables you inject, the more confusing they're going to get, and that increases the likelihood of incorrect translations. For localization, almost everything we interact with day to day is referencing the ICU for C or for J under the hood, but ICU for C is referencing CLDR. And so all of that is sort of bundled into some kind of binary in these libraries. But you have access to the same data. So if you ever are coming across something at work, check the CLDR, see if they have some kind of like answer for that, and you can like make your own library just by referencing their files. So canonical equivalence, collation, not normalization, and encoding are some more topics. If you find this interesting, that's like a whole other, each of these could be their own talk. Lokalise is offering a free trial if you're interested. There's a lot of TMS vendors. I genuinely do like Lokalise. I directly refuse like any money to have any signups for them. They're just the best vendor that I've worked with in this industry. And again, a lot of it is because a lot of the other vendors want you to use their stuff and like keep you forever. Whereas Lokalise just has like webhooks. They have the generic version of all these integrations you would want to do, and they do have libraries, so like you can add quick scripts like you saw. But that's basically it. So appreciate you all being willing to like deep dive into some Unicode nerdiness. But any questions?
If I want to localize my code, my backend code, Django, I don't need to write a single line of I need to import anything from Lokalise, right?
Whoa. No, if you're localizing your backend code, you don't need to what now?
Need to import any library?
No. So it depends. Like, for example, that Grapheme library I mentioned, that might be an example that you might want to install it externally, or like pip install it or whatever. So dealing with strings is where you're going to have a lot of the most common problems day to day in your code base. Oh, for translation, I would say it depends on your framework. So, for example, like a lot of frameworks have translation support out of the box. So no, I would say use whatever your framework recommends, and then your vendor, your TMS vendor, if they don't support that file, then don't choose that vendor. But that would make your life a whole lot easier. The good thing is that Lokalise and a lot of them, like there's some pretty common standards around translation files, and so you're probably going to have support if you're not using some kind of home-rolled framework. It's 99% sure that your vendor is going to support your translation format. Thoughts, questions? Yeah, so the pre-composed characters are pretty much anything that existed in a legacy, like before Unicode started growing. So I would say I don't really know the answer of like what is pre-composed and what isn't, but I do know, for example, like in some of the CJK characters, you saw in one of the scripts how there was like a little circle dot and then a tilde. There's that version for like CJK characters where you merge them together, and there's just so many combinations that really the CJK character set are the ones that don't have like a pre-composed version. And so it's typically like the ASCII with the tildes and stuff like that that has a pre-composed version. Is that your question?
Yeah, I was wondering about this because I was wondering like if you have a column in a database and you mentioned that like var characters only have characters, how would you know like what var char size to give your column if you want to guarantee
Yeah.
example that to be kind of roughly?
I recommend rounding up. Just like, that's really the best solution. Yeah, kind of pray. But then on the on your code side, you could validate for that. So you could say, hey, I'm receiving a new value. I'm about to store it to my database. Count the graphemes instead of counting the characters. And then you could probably throw an error that way before it even gets to your database. And then, yeah, that's a good question on how to like check existing data to see if that's occurring. I mean, at the end of the day, you could use those very terrible like property names and their value and figure out like the last character in every database field. Does that indicate that it's a decomposed character and that it's expecting something else? But to be honest, I don't know if there's a great way to solve that if like for existing stuff, depending on the context. Cool. I feel like you're a doubter. I feel like you're thinking through it. I like it. Cool, well, I'm going to be at the Lokalise booth the rest of the day, so definitely come hang out. I'm happy to talk about this more. Thanks, everyone.